first thing is we have to start our tool, and the first thing is that we should go to the workspace uh, where this tool is located, and the last command to invoke the tool is virtuoso space ampersand. Now the first thing is this is the library manager, and this one here is the virtuoso log. uh, the errors that we will get during our simulation, those can be found here. Now, in library manager, this is the libraries. They contain technological file libraries, analog library, basic libraries, and user-made libraries. And these are the cells inside the library, and inside those cells the features can be viewed under this column view. The first thing that we have to do is we have to create our own library. So in order to create our library, go to File, New, and Library. I will name the library as Demo TK, and press OK. Now it will ask that we have to attach technology file for the new library that we created. Now there are various options. The one that we are using is attached to existing technology library that we have here, and press OK. Here we have to choose the technological library. It is GPDK045. That is, it contains 45 nanometer technological file. Press apply and then OK. Our library is created. We have to select it, then go to File, New, Cell View. Uh, Once you click on Cell View, you will get this pop-up. It will ask to name the cell. I will call this as transistor underscore demo, and I will open it with schematic L. There are various options here, but in order to uh, proceed to layout, we will be starting with the schematic L. There are two options here, schematic L and schematic XL. Since it's our first, so we will start with schematic L and click OK. Now this opens our schematic editor window. This toolbar contains various functions. We will be seeing those as we proceed with our analysis. The first thing that we have to do is we have to create an instance, or we want to place a transistor. So for that thing, you just click here, create instance, or small I is the bind key, and once you press that thing, you will get this pop-up asking to add the instance. Now we have to browse to find our instance. Now this is the technological file library. In it, these are the various cells. I have to find PMOS cell. I write PMOS here. Here it is. I will select this, and these are the various uh, things associated with PMOS. I will select the symbol. Now I will close this. Now this is my MOS instance having these parameters. By default, it will have one multiplier and one finger. The channel length will be 45 nanometers, and the width will be 120 nanometers. Now hide it and place this. Now this will continue to place these MOS. We don't want, just escape to come out of the MOS instance. I will again add an instance by pressing I and browse now again. Now these are the various variations of PMOS 1 volt. Here is we have PMOS 2 volt, and close this thing and hide this, and I will place here and escape to come out of this mode. Press F to fit the screen workspace to the screen. Now you can view that you can visualize the difference between 1 volt PMOS and the 2 volt PMOS. We call this as a thin oxide PMOS and this as a thick oxide PMOS. The channel length here is 45 nanometer. Here the channel length is 150 nanometers. Here the width is 120 nanometers, and here the width is 320 nanometers. It's for high voltage, it's for low voltage signals. For now, if we save it here, we will get this warning here. There are no errors, but there are 8 warnings. To visualize those warnings, go to Virtuoso log window, and you will find these are the warnings here, and they are because of the floating connections. The other way of checking these warnings is to go to chunk, find marker, or simply press G. Again you will see these things. Now in order to mitigate these floating connection warnings, we have different ways. I will explain them. First is to we will add pins to these terminals. So I will call that those pins as D as drain space, source space, gate space, body. This is my drain, this is source, this is gate, and this is a body. Now I have to connect them here. One way of connection is simply take a wire here, create an arrow wire, or press W, and this is the drain. I will connect it here. Sorry, this is source, not the drain. Now how can I say that one, there is arrow. The second, I can click on this thing, right click, and then descend, or just press E, and here I don't want to edit, I just want to read this symbol. So this is source, gate, body, and drain. Then again control plus E, or right click and return here. We will reach back here. So I was telling to we have to connect these terminals with these pins. So press W, and we have here gate, and I will just connect it with here. Right? I can do this with here, and source here, and body here. Uh, Let me do with the source, since it is fine. Now drain is here, body is here. If I try to make a connection, it will make this schematic look very um, not a clean schematic. So to make a clean schematic, press W and take a connection here. Double click, click, double click, and escape. Now I will use label. Uh, in order to use the label, the shortcut key is L, and here I will write B space D. B for body, D for brain, and put B here label and D here. Now if I save, now I have only got 4 warnings. This structure is complete. There is no warning associated with this thing. Now only 4 warnings are there, and they are because of this thing, because we have not made any connection here. So I told you that we have to make the connection with the pins, or I can do one more thing. Uh, Add instance by pressing I, browse. Here I will go to basic, and here we have no connection here. I don't want to make any connection, so I will place these pins here. Then R to rotate, place another no connection here. Rotate R, place connection here, and rotate, place another connection here. Escape to come out of this mode. Now save. Now there is no error associated with this schematic. You can see here, schematic check completed with no errors. I can press G and there is no marker here. Fine. Now I saved this thing. Now I will go to launch, click on layout XL. Here we are asked by this pop-up that physical implementation will take place. We want to create new. We don't have any open existing, and the configuration will take place automatic. Just keep it here. Just check it whether the application is layout or not, and we will get this layout window now. Now, in order to get the devices, the instance from our schematic to our layout window, we have to go to connectivity, generate all from the source, or here we have this icon here in the lower toolbar. It says generate all from the source. Check these things. For now, just move on. Just there is this IO pin. If there is any metal connection, it will be made of metal 1 default. If required, we can change it, but for now we don't need to change it. We just place it here. So we have PMOS 1 volt and PMOS 2 volt. Now in order, this is just the block view, outer line view of PMOSes. Shift plus F will give us the internal structure of the two MOSes, and then we have 4 pins that we used. Although we have only used 4 pins with this MOS and no pin is used with this MOS. That's why we only have 4 pins. To cross check, let us cross check. So I will click this. It is drain, this is source, this is gate, and this one is the body. Okay, and there is no other pin here. Now what is this? This is PMOS, this is PMOS 2 volt. As you can see, they are of different sizes. Obviously, in the schematic we have seen that the two are of different sizes. Here the channel length is 45 nanometers. Here the channel length is 150 nanometers. Here the width is 120 nanometers. Here the width is 320 nanometers. So we will see whether in layout we are getting the same things or not. So for that thing, we have to use here layers. So these are the various layers that are available to the user to design a layout, but we don't require all the things. We will just click here, use layers only. Now we will get the layers that are used in this layout. AV stands for all visible, none visible, all selected, none selectable, and V is select visible and S is selectability. Now what we are going to do, what I am going to do is I will uncheck them where I can show you properly that how this MOS layout is done. So first thing, our device, our transistor here was a PMOS, right? This was PMOS, this was PMOS. So this is PMOS. Now, we know in PMOS the substrate will be N-type, right? So for PMOS 1 volt, this is the substrate, and for PMOS 2 volt, this is the substrate, right? When here you can see it is annual, so this is annual of PMOS 1, and this is the annual of PMOS 2 volt. We can check the size of the two by clicking by pressing the K key and measure the dimensions. So you can see this dimension is 0.24, means it is 240 nanometers, and horizontal is 0.44, it is 440 nanometers. 0.24 in micrometers and 240 in nanometers. Likewise here we have 0.8 micro or 800 nanometers annual here, and this dimension is 0.93, 930 nanometers. Okay. To remove these scales, shift plus key removes those. After this thing, after we are done with creating a laying down anvil, we place oxide layer. Now oxide layer is an important layer. uh, it will be placed inside the anvil active region. This oxide is the active region of the device. The active region is where the channel and the transportation takes place. So this oxide layer, if I zoom it, its dimension in the vertical side is 0.12 micrometers, or it is 120 nanometers. We have seen here that the width of our PMOS was 120 nanometers. So when we are talking about width here, we are talking about the width of the oxide or the active region here. The length will be adjusted as per the gate and source and drain and contacts. So it is 0.2325, means 325 nanometers. Now let's go here. Let's check the dimensions here. It is 0.32. What was the width here? It was 320 nanometers. Here it is 0.32 micro, so it will be 320 nanometers. So vertical direction is the width, and this dimension is around 0.45. The direction which we are interested is the vertical here. because that is the technologically specified that the width of PMOS 1 volt should be 120 nanometer and the width of uh, PMOS 2 volt should be 320 nanometers. When we place this oxide, then uh, it is neutral. Oxide is a neutral layer. Now we know in PMOS the active region will be p-type. So we have to then place P implant here. This is the P implant on the two devices. Note the P implant is outside both active oxide layer as well as the anvil. Here you can also see, okay, here it is inside the anvil. Here it is outside, here it is inside. Uh, the important is it does not matter whether our implant is outside or enclosing the anvil or not. The important is that it should enclose the active region. That's more important. And there will be a design rule error if we are not maintaining that. Okay. So let me see from the active area edge to the edge of the implant, it is 0.07. And let's check here to the edge of from the edge of active to the edge of implant, it is 0.07. So we are just maintaining the minimum distance from the active area to the edge of the P implant. That's why our anvil came inside here, our anvil is outside this implant area. Once we are done with placing the implant, then we will place poly region. Fine. Now, before going to the poly region, here we have to include the oxide because I told you this is thick oxide transistor. Now, this layer is not with this MOS, PMOS one. It is only used with the PMOS 2 volt, as you can see. Now, this is the layer oxide layer that is added to the PMOS 2 volt, and let's check from the edge of the active region to the edge of the oxide, it is 0.16. That is 160 nanometer oxide layer is added here. Then we add the poly. We are adding the gate. Uh, the channel is in this direction. The width was vertically. The channel will be horizontal. So let me check the size from edge to edge. As you can see, it is 0.45 and our channel in PMOS 1 was 45, and here from edge to edge it is 0.15. We will check here, it is 150 nanometer, it's 45 nanometer. So yes, so this direction it's the channel, and vertically it's the width. Once we are done with our this layer, then we place the contacts. The contacts for source and the drain. They are reversible. We can consider this as source and this as drain, or this as source and this drain, vice versa. And here we are taking two contacts because the size of the active region is more. So we are taking more contacts here. More contacts is better because it helps in proper distribution of current, and less heating and noise will be generated. And once we place the contacts, the contact size here is from edge to edge it is 0.06, and from here 0.06. So it is 60 nanometer by 60 nanometer, and here it is 0.06, and here it is 0. So contacts are having the same dimensions for PMOS 1 volt and PMOS 2 volt. And once we are done with placing the contacts, we have to take the connection to the metal wiring or traces. That is done by placing a metal strip on this contact. The metal one is enclosing our contact here, and metal strip is enclosing two contacts here, right? I hope this is clear. Now I will update this. Select this, press Q. Then here I will select 2. Now initially there were only one finger. Now I am increasing fingers to 2. As you can see, my width changed from 120 nanometers to 240 nanometers, while the length remains same. Now we will see what will be the impact of this finger here on the layout. Now we have this, and let me check whether it will get updated or not. Okay, yes, it got it. So here we have our device now with two fingers, one finger and two finger. Now we got three contacts here. It can be source, or drain, source, drain. Let me try to. There was this option of drawing. Mm, There was the option of drawing. I'm just checking that. So where is it? Looks like we don't have here. So, uh, so I was telling that with two fingers we will get this device. One finger is this, second finger is this. Now this can be source, this can be drain and source. So one of the terminal is sandwiched, and at the outer side we get the other terminal. This can be source and source, then sandwiched is the drain, or this can be drain and drain, this can be source, depending on the design, how we want to use them. Okay, now again, uh, let me select this, press Q. Now I will change to multipliers now to 2 while changing the finger back to 1. As you can see, the width is now back to 120 nanometers. Channel length is same. Apply. OK. And let me go here. I will select this, and I will see whether this will get updated. Yes. Okay. Actually, it did not get updated. What I will do is I will delete this, and I will also delete this one. Now go to connectivity, generate, selected from the source. From the source I want this thing, and I will place it here. Now with two multipliers I am getting two MOSFETs. PMOS is one PMOS and two PMOS. So when I am saying that we are using two multipliers, we are using two MOSes. Then we can combine them as we did, as we saw in uh, two finger cases. Hope this is uh, okay. Now next thing which is here is this gate connection. I will select both gate connection both, and top and bottom, and save it, and go here, go to connectivity, see if it gets updated. No, did not got updated here, so I will just delete them, and here I will generate selected from the source. Go to here, press this one now, and place them here. Okay. I will also delete this one and this boundary because I don't require now. Now you can see I got two MOSes because I have selected two multipliers. I have selected two multipliers, that's why I'm getting two MOSes for this thing, this here, and we have got the gate connection both at the top, at the bottom. There's no connection on the channel, and it is because no connection can be made on the channel because when contacts are made, they involve heating process. If the heating takes place on the polysilicon, it can damage the gate. That's why the contacts are made on the top and the bottom side of this polysilicon. Another thing here with this MOS is body tie type. Currently it is selected to none. I can select integrated, and I will choose left tab and OK. Then I will go to connectivity to see if it gets generated. Yes, it got generated. So we have two MOSes, MOS 1 and MOS 2, because we have selected two multipliers still, and we got the third contact here. You can see we have this is the body contact and it is tied here. It means now this will be source, this will be drain, and this will be the body contact. In default cases, source has to be tied with the body contact. That's what they are tied together. You can see here. Okay. Uh, I can also do, I can select body type currently is integrated. I can select detached and I will choose the left tab location, means it will be placed on the left side. Then here go to generate, sorry, update components, and then parameters. Now here to move, select, then press M, then click on the instant that we want to move, and that will move. Right? As you can see, now we have got this body contact, and that is separated from this device. Earlier it was attached, now it is detached, and here we got two contacts, and they are not now this is not tied here, so it can act as source or drain or vice versa, and this will be body contact. And again, there are two contacts with the body, and it's better to have more contacts because it helps in the proper distribution of the current, and less noise will be generated. But in designs, certainly we don't place the detached or integrated. We place this transistor with body type none, and we generate our own body type. This body type is nothing but a connection to the substrate. Right? Here we have same, we have multipliers, we have fingers, and gate connection, again top, bottom, or both. Then body type, integrated, detached, and various other parameters that we don't require to analyze because we have already done that. Hope you understand this one.